chat. I will try and monitor it. I'm Andy Gordon. I'm the session chair. But at this point, I'm delighted to hand over to Atilim Baydin from the University of Oxford, who does lots of cool stuff around differentiable programming and probabilistic programming. Take it away, Atilim.
All right, thank you, Andy. So I'm sharing screen again. And I forgot to say good to see you. All right, okay, so I'm going to assume this is fine. Please let me know otherwise. So the talk is about probabilistic and differentiable programming. And I think it is slightly different from the rest of the talks because it is very application focused. I know many of you in the audience are interested in like technical like problems and implementation, or like basically theoretical part of these aspects. But I've been recently working on highly like in collaborations that are completely focused on applications, basically. So the talk has two parts. Most of it is about probabilistic programming and applications of it in existing large-scale scientific simulators. And I'm going to also have a little bit of component in the end, covering some bits of differentiable programming and how this also applies to like applications in science. So yeah, most of what I've been doing recently is about applying probabilistic programming in science, and I'm going to explain why this is possible and interesting. So in many fields of science, let's say fundamental physical sciences, people work with computational models and simulation. These are actually key to like many of these fields, ranging in scale from particle physics in the like smallest scale, all the way to like climate science and cosmology in the largest scales. And so my work has been bringing together probabilistic programming and simulation. So to introduce the subject, like very briefly, we can talk about what the simulator is. Simulator is a piece of software that takes some parameters, it runs, and it gives you some output. This output, in many cases, corresponds to data that you can actually observe independently. And you can use the simulator in basically two ways. You can run the simulator forward. We can call this prediction. So the simulator simulates the forward evolution of a system. This thing actually, like in many cases, corresponds to the arrow of time. And you generate some samples of output. And this is interesting in fields where you are interested in making projections into future or predicting things, such as climate science, let's say, or like modeling of floods or folding of proteins. But in science, in many cases, you need the inverse. That's a very interesting direction. And this is what we can call inference in this context. Basically, we are given some observed data that corresponds to the output of the simulator, and we are supposed to find some distributions over parameters or like the things internal to the simulator that explain, that can produce and therefore explain the observed data. This is an inverse problem. It's a manual process often, and it is actually difficult. So some examples of these are maybe in seismology, you have forward models of how waves propagate forward in the crust. You are given some seismometer readings and you are supposed to infer earthquake locations and characteristics. Or in particle physics, which is a field I've been working in, you have some particle detector readings and you want to infer what's going on inside the detector. So I think many of you start to see the connection. Probabilistic programming is a perfect tool for this type of questions because in probabilistic programming, we write programs that define models, probabilistic models, and we have a capability of doing automated Bayesian inference conditioned on data. So the thing is, probabilistic programming has been limited to toy and small scale problems mostly, or in my view. And I believe this is mainly because these probabilistic programming systems and libraries require people to implement models from scratch in a chosen language. And you cannot go ahead and implement some very detailed, complex particle physics simulator that took like decades to develop in let's say Pyro or Stan. So the key idea in the type of work I'm doing is to realize that simulators, like almost all simulators are stochastic in nature, and they actually define probabilistic models by sampling random numbers. So they incorporate, or like they implicitly define probability models, even when the people who implemented the simulator did not have this type of intention. So if you have access to the simulator code, the source code, and if you can identify places where this like random sampling happens, we can actually treat existing simulators as probabilistic programs without having the need to re-implement them. So in order to do this, you need some software infrastructure to execute existing stochastic code bases as probabilistic programs, basically. So I've been working on a research prototype system called PyProb. This is yet another probabilistic programming library. It's based on PyTorch and Python, but this is designed in a way that allows you to connect it to existing simulators in other programming languages running on other machines, and like basically you can mix and match different stochastic models in different places and runtimes to this probabilistic programming system that is running in Python. So I don't have a lot of time to go into detail, but like I'm going to cover how this works at a high level. Basically, we are going to do a probabilistic execution of an existing simulator code. What we do is we run the simulator forward many times, and we catch all the random choices. We can also call this a hijacking. Basically, we have a way of intercepting all the calls to the random number generator in the simulator's code base. And once you have this, you can record an execution trace. And execution trace is basically a record of all the stochastic choices that happened in the forward simulation, or like forward execution of the code. So if you have this capability of before that, actually, in order to do that, you need to have some sort of infrastructure to achieve this, and this is what we call the probabilistic programming execution protocol. This is basically a very lightweight protocol based on flat buffers that basically has a compiler that gives you code in all major languages that I'm listing here below, to basically connect your existing code in any of these programming languages to the PPX protocol. So once you make that connection, meaning that once you redirect your random number samples in these languages to this protocol, basically we have the capability of recording these execution traces. That's the highest level, shortest summary I can give, given the time limitations. And this thing has been inspired by the ONNX, or the Open Neural Network Exchange protocol that people use in deep learning libraries to exchange data or models. Another thing is, in the probabilistic programming side, you need some addressing scheme to uniquely label each choice, each random choice or random sample or like latent variable at runtime. So in this example I'm showing here is we have an addressing scheme that is based on concatenation of stack traces in C++. This is from a C++ simulator. So once we have this capability of uniquely identifying latent samples in the code base and recording execution traces, we are almost there to treat the simulator as a probabilistic program. And the only remaining limitation, or the only remaining requirement to call something probabilistic programming is the conditioning part. That is basically a way to compare simulated output with observed data with a likelihood distribution. So once you have these pieces, basically you can do inference using all the tricks in the book of probabilistic programming. You can do MCMC, you can do importance sampling, amortized inference, like the variety of inference engines can be brought here. So there is one big problem when you treat an existing, potentially very large scale simulator as a probabilistic program. Inference is very hard and it's computationally costly because these simulators correspond to giant, really big, not before seen type of probabilistic programs in the probabilistic programming side. So, and the thing is, and we are doing approximate inference, we need to run the simulator up to millions of times. With MCMC, we have like a lot of problems with burn-in and autocorrelation, depending on the problem scale. So an important part of the work is to basically make this feasible in practice. And this can be done using amortized inference and using some deep learning based way of proposing, learning some proposal distributions from the simulator. So this is a little summary of how that type of thing can be achieved. So there are two phases. In the beginning, we have a training phase where we basically run many copies of the simulator, which you can do in a distributed way. You record these execution traces. And one thing I need to remind you is that these traces are different in length and different in the ordering of addresses, because we are working in a universal probabilistic programming setting. So we record these sequences, the traces, and from this we can train a proposal network, basically, which is a type of recurrent neural network, where we invert the structure of the trace. In many cases, towards the end of the trace, you have random variables that correspond to data. We make these random variables an input to the network, in each case in the training, and we ask the network to give us proposal distributions under which the probabilities of the other random choices in the trace are maximized. So once you do that, and you have to do this only once for a given simulator, you are left with this trained neural network, which is very costly to train. Then you can use this in an amortized inference way by basically taking this trained neural network that's specialized into that simulator code base, and another like ingredient, which is the observed data. So basically, you are given an observed data, you condition on this observed data, and you want to get distributions, posterior distributions over basically everything in the simulator. You do that by taking the observed data, plugging it in to the input to the neural network, and executing the simulator together with the neural network in a way where the probability distributions in the simulator are replaced by the proposal probability distributions that are given by the neural network, meaning that we execute these two pieces side by side through the protocol that I mentioned, and the network basically guides the simulator to make it create data that is as close to the observed data as possible, based on its history of seeing lots of like training traces. So this is like a very high level overview of how we can do amortized inference. And another way of thinking or talking about this is you have the probabilistic programming system that somehow like controls, or like a puppet master controls the simulator or guides the stochasticity in the simulator to make it work in different ways. And in order to achieve this, you need some software engineering type of work, which is actually quite difficult to set up like in the beginning, but we have all of that already done. So there are several pieces for people who are interested. So this PyProb thing is like a Python probabilistic programming library. Interesting thing about it is it has this distributed training and inference code in it, and it also supports code. It has code that can work with like very, very large distribution files. When I say very large, I mean like multiple terabytes of empirical data. For example, let's say you work with a particle physics simulator, which is very big, million lines of C++ code. You take it, you treat it as a probabilistic model. Then if somebody gives you a piece of observed data and you want the posterior distribution, that posterior distribution can be several terabytes because of the size of this model, because the model corresponds to tens of thousands of latent variables. So we quickly realized this type of stuff is not available in the probabilistic programming community, so we had to implement these things. So there's the probabilistic programming part. There is this protocol that we call PPX that I mentioned, with all these languages supported. So this is something completely independent. People can connect to this protocol either from the simulator or the model side, or from the probabilistic programming side, to basically mix and match these models and probabilistic programming systems on the two sides. And like there's a yeah, the last bit is not so important. This is just like a C++ connection to the PPX protocol, because in the beginning we work with C++ simulators.
Atilim,
yeah,
we have a question in the chat, in
yes.
the Q&A. Oh, there it is.
Yeah.
Go ahead. You can just answer directly, and McCoy, if you want to.
I can't read it. Sorry. Can I?
Oh,
let's see. Andy, could you help me by reading the question? Okay.
yeah, sure. It's the question is stack trace based addressing a limitation for inference techniques that utilize custom proposals or guides?
No, unless I'm missing something important in the question. No, I mean, no, it's not. Yep, that's my short answer. I'm very conscious of time. Sorry, but I'm willing to like talk about this more maybe after the talk with the person who asked the question.
I'll let you get on. Thank you.
Yeah. Okay, so I'm a bit worried that maybe I have too many slides for the talk duration. I'm beginning to realize that. So this is how the protocol works, but for people who are interested, like basically there is like an exchange of messages. The probabilistic programming site controls everything. Basically starts, it says like it starts the simulator. The simulator keeps running. All these things are like these arrows represent deterministic execution. We don't get to see that. Every time the simulator needs a random number, like sampling something from a distribution, the request goes to the Python side over the protocol. It says, okay, I want a Gaussian with this mean and standard deviation, let's say, or any distribution. The Python side does the sampling, returns a number, but it also does the bookkeeping behind the scenes that you need to do, basically this trace recording. Basically, that's all there is. The protocol is very lightweight. Yeah, this is an example of how things look in C++. It's like your typical average probabilistic programming system that works in C++. An interesting thing is there is no probabilistic programming library in C++. All these things like the sample statement, the observe statement, all this stuff, they just are communicated to the protocol and they end up on the Python side. So there is no inference engine in the C++ side, for example. That's maybe kind of interesting because I don't know if other people do that. Yeah, so once you do this type of thing, the protocol allows you to connect from the probabilistic programming library to the simulator using the protocol. So this thing can go over TCP. The model can be running on a different machine over the network. It could be anything, like in any language. So if there's some sort of handshaking, once you do that, you basically treat this model as a probabilistic program, which you didn't implement in the Python side, but it's there. You can sample from it. You can do inference. You can do everything you usually do in probabilistic programming, basically. Yeah, so I have some material to talk about the particle physics application that actually led us to develop all these tools. So in the beginning, we started working with particle physicists. And these people, like particle physics people, they have very large scale simulators that basically correspond to the physical processes and the instrumentation at the Large Hadron Collider. And the short summary is that we work with a simulator that's called Sharpa. This is a simulation of the standard model of the particle physics. And we worked on a problem involving the decay of a tau lepton that has some connections to the Higgs boson. So it's scientifically very exciting and interesting. And basically, the simulator was so big and we needed so many samples and like a lot of work. So we initially developed all these tools to run on a supercomputer. We basically had some support from Lawrence Berkeley lab, and we used the Cori supercomputer to basically deliver the first tractable Bayesian inference for Large Hadron Collider physics. So this was the beginning of all these tools and approaches that I'm presenting to you. And the overall thing that we are trying to do here is, so you have your simulation or probabilistic programming pipeline, and you have your real-world system. Basically, the idea is the pipeline gives you simulated data, which parameterizes the likelihood. And ultimately, you have some real data that corresponds to the simulated data, like omitting questions of like simulation to reality gap, which is actually an interesting subject in a model such as the standard model. So you have this likelihood, you have all the priors implemented by the stochastic simulator code base already, and basically in the typical probabilistic programming fashion, you get the posterior distribution over tens of thousands of latents in this Sharpa simulator in C++. These are some examples of how these addresses look like. We give them short names like A1, A6, A2, whatever, like because these things are very long. And yeah, I think I'm going to skip these details. So at the end of it, you can do several inference engines. For example, Monte Carlo, Markov chain Monte Carlo. If something took like 100 hours, we can do that like in like arbitrarily small durations, because this amortized inference part is embarrassing the parallelizable. So we have an example where we made these like produce posterior distributions in under an hour, which was a big improvement. Yeah, so there's another thing to remind you here, because we have distributions, posterior distributions over like tens of thousands of latents. There is a aspect of the work that is about interpretability and looking at the results. For example, you can choose some subset of the random variables that are interesting for physics, but if you want to look at the full picture and what's going on inside the simulator, like the representation and interpretation of these results is an issue, and it is actually an interesting area. So I don't have time to go into detail, but so if you see this thing on the right hand side, these are loops in the graph that corresponds to basically 4 loops in the source code. These are rejection samplers sampling something until some acceptance criterion is satisfied. So we started with this type of things, and we developed some summarized representation of the probabilistic structure of the simulators through the protocol. Basically, you can introduce cycles showing like repetitions of the sampling for an address, and showing you like what sorts of things can happen inside the simulator. So this is something you like. This graph is an example of that particle physics simulator, taking into account the 10 most frequent trace types. And these are interpretable because you never discard the simulator. That's basically your probabilistic program. And people who know this simulator can read these things and actually understand what's going on and where in the code base these things are. So if you take more and more trace types into account, you get a more and more detailed view or like insight into the probabilistic structure of the simulator code base. And this is what I'm trying to show here. Yeah, so this is one of the interesting aspects of the work, because it allows you to uncover the probabilistic model hidden inside the potentially giant simulator code base. So there's an extension of this to probabilistic surrogate models. I think I'm going to skip that, but the idea is to make use of this structure as a substrate to learn a completely deep learning based replacement or approximation of the whole simulator, because these simulators are in many instances very slow. So we can actually use the traces that we record from the simulator, discover this structure, and construct networks that exploit this structure and the data already sampled from the simulator to basically learn a complete replacement of the simulator. Not in a way that people do in deep learning, like we don't do a black box approximation. We have an approximation of it that completely maintains the stochastic control flow and the address structure of the simulator. So this is something interesting. I'm going to skip all of this and finish by a couple of things about differentiable programming. Yeah, so I wanted to put this thing here because like we have people in the audience that work on differentiable programming or automatic differentiation. So I have this DiffSharp library, some of you know. It is a library in F#, and the main features of this is nesting of forward and reverse mode, and this higher order API. This is something I started with Parag Parameter and Jeff Siskin. So this is just like a little news / update type of thing where I mean, I just want to tell you that I'm currently re-implementing DiffSharp with Don Syme from Microsoft. We are actively working on this. We are basically introducing tensor backends, like modernizing the library, basically keeping all the good things from the earlier versions. And we do that by using libtorch, the core C++ and CUDA code in PyTorch without the autograd part. We take the tensors in libtorch and we implement our own computation graph and differentiation code on top of that in F#. And this supports like all operating systems and GPUs basically. And you can use this in things like Google Colab and Jupyter and all of that. So it's like a little update. And I would like to finish by talking about several efforts that I'm involved in for using differentiable and probabilistic programming in science applications. This is for inviting you basically to join these efforts if you have time and interest. Like we are really looking for collaborators from the computer science community to join these efforts. One of them is the MODE collaboration. It is about optimizing the design of next generation instruments at CERN. And this we had a workshop in September where we basically brought together like computer science people with the particle physics people. We had people from Google, such as Adam Paske or Fritz Obermeier from the probabilistic programming community from Pyro. So we want to repeat this. And the idea is that you can influence the design of experimentation hardware which could potentially like giant impacts in like cost reductions and other things. And lastly, we have a program that will take place like next summer. It's the 1 month residential program. Basically, again, at the intersection of this CERN particle physics community and the machine learning or automatic differentiation community to basically host people in Munich for a month and like work on some problems together in a hands-on way. So we will have a website for this appearing very soon. Yeah, that's basically it. I'm a bit over time. Sorry, Andy. That's all. I think maybe we can take some questions.
Great.
Yeah, it was too much. Yeah, I had too many slides. I guess. Yeah. Okay.
Thanks for your talk. We've got about 3 or 4 minutes
All right.
before the end of the slot. I had dropped a question into the Q&A, but really, everyone here do consider asking a question. My question, Atilim, was well.
Yeah.
Firstly, I thought when you were talking about the work, maybe it was from a few years ago about the I guess modeling the LHC physics.
Yeah.
I thought this is amazingly cool, just amazingly cool that
Thank
you're
you.
doing this. But I just wondered, from the perspective of the physicists, you're saying it's the first tractable Bayesian inference for LHC physics. I wonder, what's the alternative for them? I mean, what difference does it make to the physicists?
Yeah, okay. So it's actually like that community is very conservative, and even doing like basic machine learning things is like very big steps for them. Like there are people like Kyle Cranmer, maybe you know him, or like some of my collaborators that are trying to transform that. Even doing something Bayesian in particle physics is like a very big step that almost is non-existing in particle physics. Some subfields of physics are fine with that, but particle physicists don't do that. So to answer your question, the state of the art is manual, cutting data in some bounds influenced by your domain knowledge, running some set of simulations, putting things in histograms and seeing if there's a bump in the histogram or not. Like all of it is manual, basically, as far as I understand. And there is nothing automated or no inference frameworks or like setting up inference questions and stuff like that. Things are manual in many cases, very labor intensive. Yeah.
Wow.
Yep. Are there any other questions? Maybe I missed in the chat. Let's have a look. Perhaps not.
There are lots of folks in the session, but they're quite quiet. Does anyone have a question? You can raise your hand and ask it directly. Oh, someone is asking. Sam is asking. Any chance of making a PPL over DiffSharp?
Yes, I have a prototype, and like several people actually asked me the same question. I think Maria Gorinova, I think she used DiffSharp for a project. We had a couple of meetings with her.
Yeah.
I think she can answer that. I don't know if she's in the audience. She has a talk later, right?
Yes. Yes.
So maybe if we are lucky, there's something about DiffSharp in the talk. But yeah, I have my own like little prototype working basically just with basic importance sampling. And yeah, I'm super interested in like that direction, and Don as well, like Don Syme. That sounds super cool. Maybe I can repeat my invitation to the community here to these like collaborations and workshops and all of that. Like if you are interested in applications, like you are very welcome to get in touch. And like there is really a need for probabilistic programming and autodiff experts in that site and really influence some science questions. Yeah.
So Maria is actually on stage. Maria, do you want
Oh.
to respond to Atilim?
Hi.
You
Am
have
I?
about 20 seconds.
Okay, so yeah, I just wanted to say thanks for pointing the audience to me. Yes, I do have a prototype of a PPL over DiffSharp. It is, I haven't touched it for a long time, and it is in a private repo, but maybe we can schedule a meeting and talk about it again. I would love that.
Sounds good. Yeah, sounds very good.
Cool. And thank you for the talk. Great talk. Super interesting work. As you know, I really love this work.
Thank you. Thank you. All right.
There are a couple of questions in the Q&A, but maybe we can take them offline because Atilim, we need to move to the next speaker. But let me just, on behalf of everyone, just thank you again for a fantastic talk. Thank you, Atilim.
Thank you, Andy.